a aldehyde and ketone that contain all the important concepts that you need to know. Aldehyde and ketone. We begin our study of carbonic compound with the study of aldehyde and ketone. Carbonic compounds are molecules containing the carbonyl group, which is C double bond O. This includes aldehyde and ketone, two double bond, two heteroatom. Carbonyl group also are being represented by carboxylic acid, C double bond O and OH, and also carboxylic acid such as ester, anhydride, acid halide, and amide. Nomenclature of aldehyde and ketone. Common names are used for the simplest aldehyde and ketone. For example, formaldehyde, butyraldehyde, benzaldehyde, acetone, acetophenone, benzophenone. Common names are also used for carbonyl-containing substituent groups, which are known collectively as acyl group. For example, formyl, acetyl, and also benzoyl. Traditional names are used for a great many aldehyde and ketone which were recognized as substance long before systems of nomenclature were developed. The examples are shown below. For example, cinnamaldehyde, furfuryl, and acrolein. Three of the four bases which comprise DNA contain carbonyl group, and all four bases are nitrogen heterocycle, which we will discuss later. The examples are illustrated in below. Guanine, G represented by G, thymine represented by T, and also cytosine represented by C. All these three examples are the base of the DNA that contain C double bond O group. Structure of aldehyde and ketone. The carbonyl carbon of an aldehyde or ketone is sp2 hybridized. The bond angle is close to 120-degree trigonal planar. The carbon-oxygen double bond consists of alpha C O bond and alpha pi C double bond O bond. We can compare the C double bond O bond length to those of C double bond length. The examples are illustrated below, which is represented by formaldehyde, acetaldehyde, acetone, and also propene. Properties of aldehyde and ketone. Aldehyde and ketone are polar molecules because the C double bond O has a dipole moment. For acetone, dipole moment is equal to 2.7, whereas the boiling point is 56.5 degrees Celsius. For propene, the dipole moment is 0.4 and the boiling point is minus 47.4. For isopropanol, dipole moment is 1.7, whereas the boiling point is 82.3. Their polarity makes aldehyde and ketone have higher boiling point than alkene of similar molecular weight. Aldehyde and ketone are not hydrogen bond donor, which means they can donate a proton. Therefore, they have lower boiling point than an alcohol of similar molecular weight. Aldehyde and ketone are hydrogen bond acceptor, and then therefore this makes them have considerable solubility in water. This example illustrates The ketones such as acetone are good solvents because they dissolve in both aqueous and organic compounds. Recall that acetone is a polar aprotic solvent. Reaction of aldehyde and ketone. The reaction of aldehyde and ketone can be divided into two main categories. The first one is reaction of the carbonyl group C double bond O, which is represented by the blue color here. And then the second category is the reaction involving the alpha carbon, which is represented by the purple color in the diagram here. Carbonyl group reaction fall into three main categories, which are the first one reaction with acid, the third one is addition reaction, and the last one is oxidation. Carbonyl group reaction. Reaction with acid. The carbonyl oxygen is weakly basic. Both Bronsted and Lewis acid can reinteract with the lone pair of electrons on the carbonyl oxygen. For example, when Bronsted acid H3O is used, we will get this reaction, which will produce a byproduct of water. Addition reaction. Carbonyl group in aldehyde and ketone undergo addition reaction. This is one of the most important reactions of the carbonyl group. This example here illustrates the addition reaction of aldehyde and ketone. Addition reaction occur by two different mechanisms. It can be base catalyzed addition under basic or neutral condition, and the second one is acid catalyzed addition under acidic condition. In some cases, we can carry out the same overall reaction using either set of conditions, whether it can be acidic or basic. Carbonyl group in aldehyde and ketone may also be oxidized to form compound at the next oxidation level, that of carboxylic acid. Alcohol are oxidized to aldehyde and ketone. Example, biological oxidation of ethanol to acetaldehyde. The carbonyl group may be further oxidized to form carboxylic acid. Example, alcohol to aldehyde, two electron oxidation, and then the reaction is further proceed, whereas alcohol is transformed into carboxylic acid, which involve four electron oxidation. Aldehyde to carboxylic acid, two electron oxidation. Basicity of aldehyde and ketone. Reaction which occur at carbonyl oxygen of aldehyde and ketone. The weakly basic carbonyl oxygen reacts with proton of Lewis acid. The protonated form of the aldehyde or ketone is resonance stabilized. This gives as an aldehyde conjugate acid carbocation character. Protonated aldehyde and ketone can be thought of alpha hydroxy carbocation, where an alkyl group replaces conceptually the proton and alpha alkoxy carbocation is formed. Alpha hydroxy alkoxy carbocation. Alpha hydroxy alkoxy carbocation are more stable than ordinary carbocation, which is being illustrated in the example below. The polar effect of the oxygen in the carbon-oxygen bond attract electron, but electron attracting group adjacent to the carbocation are destabilizing. However, the resonance stabilization outweighed their destabilization. Stability of protonated aldehyde ketone. The stability of alpha hydroxycarbocation is demonstrated by a reaction known as the pinnacle rearrangement of 1,2-diol, which is being illustrated below. Overall reaction and then how the mechanism occur. At the end, we can see that rearrangement occur because tertiary carbocation is more stable. This is show the example of hydroxycarbocation. Compare the pKa value of the conjugate acid of aldehyde and ketone with some for the conjugate acid of alcohol. The value is -7 and -2.5, the comparison. Protonated alcohol are less acidic. Therefore, alcohol are more basic than ketone. Does this make sense? This is because resonance stabilization of the protonated ketone should make it less acidic, less likely to lose proton. Hydrogen bonding explains this apparent contradiction. Protonated alcohol can undergo hydrogen bonding with two protonated ketone only with one. Reversible addition to aldehyde and ketone. Addition of water to an aldehyde or ketone gives a product called hydrate or a gem diol, two OH group on the same carbon. The reaction is both acid catalyzed or it can also be base catalyzed. The addition reaction is highly regioselective. In way, it means that the addition always occurs with oxygen adding to the carbonyl carbon atom. The tripolar planar sp2 hybridized carbonyl become tetrahedral sp3 hybridized in the addition reaction. The addition reaction is reversible. The equilibrium conversion to the hydrate varies widely and depends on the nature of the group attached to the carbonyl group. Addition under acidic condition. Addition of water to carbonyl compound under acidic condition is analogous to addition of water to alkene. The reaction occurs in three steps: protonation, followed by addition, and the last step is deprotonation, which we will illustrate in the example below between alkene and ketone. Addition of water to carbonyl compound under basic condition has no analogy in the reaction of alkene. The reaction occurs only in two steps: addition of the OH to the carbonyl carbon and then is followed by the protonation of carbonyl oxygen. Addition occurs directly because OH is more reactive nucleophile than H2O. Note that regioselectivity of addition is the same for acid or base catalyzed nucleophilic addition. Geometry of nucleophilic attack on carbonyl. The sp2 hybridization of the carbonyl compound means that attack of the nucleophile on the carbonyl carbon may occur from either phase. The resulting addition product is sp3 hybridized. We use the example of hydration, formation of gem diols, to illustrate the nucleophilic addition to carbonyl compound. However, other nucleophiles can undergo the same reaction. There are other acid-base catalyzed examples. Equilibria in carbonyl addition reaction. Carbonyl addition reactions are reversible. The extent to which the reaction is able to proceed is defined by the magnitude of the equilibrium constant. This trend can be explained by looking at the factors which affect the stability of the reactant and the factors which affect the stability of the product. Reactant stability. Recall that alkyl groups stabilize double bond. More highly substituted alkene are more stable than less substituted alkene. This works for C double bond O bond 2. Ketones are more stable than aldehyde. Therefore, the addition to ketone is less favored than addition to aldehyde. This is the comparison which being illustrated between ketone and aldehyde. For ketone, the reactant more stable, therefore the product less stable. For aldehyde, the reactant less stable, however the product are more stable. Product stability. The four groups in the product are closer together than the three groups attached to the carbonyl carbon in the reactant. Alkyl group cause more steric destabilization in the tetrahedral addition product than does oxygen. Therefore, the ketone addition product is less favored than the aldehyde addition product. Electron withdrawing group attached to the carbonyl carbon make addition more favorable. Larger equilibrium. Electron donating group attached to the carbonyl carbon make addition less favorable. Smaller equilibrium constant. Conjugation with the carbonyl group makes addition less favorable. This more equilibrium constant. Larger size of group attached to carbonyl carbon make addition less favorable. Formation of hemiacetal and acetal. When an alcohol adds reversibly to an aldehyde or ketone, the product is called a hemiacetal. Recall our example of the reaction between CH3OH and PHCHO. Hemiacetal are formed in both acid and base catalyzed reaction, acid or base, which produce hemiacetal. Note that this bond to carbon indicates that it may be either to an alkyl group or to hydrogen. Hemiacetal are unstable and can't be isolated in most cases. Hemiacetal undergo further reversible reaction under acidic condition only. This reaction involves carbocation chemistry. Formation of acetal. Hemiacetal react further with alcohol under acidic condition to form acetal. Aldehyde and ketone react with alcohol, catalyzed by acid or base, to produce unstable hemiacetal, which is further catalyzed only by acid to produce a stable product known as acetal. Mechanism of acetal formation. Under acidic conditions, some of the alcohol become protonated. The hemiacetal OH oxygen extracts a proton from the ROH2. Loss of water gives a resonance stabilized alkoxy carbocation. Nucleophilic attack by the alcohol and the carbocation occur. Deprotonization by further alcohol molecule produce the acetal, which is being illustrated in the mechanism below. Acetal as protecting group. The reversibility of acetal formation along with the relative inertness of the RO-COR linkage make acetal useful as protecting group. Protecting groups are functional groups which may be induced in a molecule. by converting another functional group in a reversible reaction. If the protecting group is more inert than the original functional group, then other reaction may be carried out with this molecule without worrying about altering or destroying the protecting group. When the other desired reaction are complete, the original group may be restored by carrying out the reverse of the reaction which introduced the protecting group, which is being illustrated in the example below. Acetal formation producing protection, and then further reaction will effect in reverse of acetal formation which lead to deprotection. Cyclic hemiacetal. Cyclic hemiacetal containing 5 and 6 carbon in the ring can form spontaneously from hydroxyaldehyde. Alcohol and carbonyl function are contained in the same molecule. Cyclic producing cyclic semiacetal, which are more stable than non-cyclic hemiacetal, which result in they cannot be isolated. They are favored under equilibrium due to high large equilibrium constant condition. 5 and 6 carbon sugar are important biological examples of cyclic hemiacetal. This oxygen here will become an OH group while this oxygen end up in the ring. Cyclic acetal. Acetaldehyde form a cyclic trimer when treated with acid. Cyclic acetal are often used as a protecting group. Reaction of aldehyde and ketone with amine. Aldehyde and ketone react with primary amine to form imine or Schiff bases. You can see here aldehyde and ketone react with primary amine to form imine or Schiff base that produce water as the byproduct. An amine is a compound with a C double bond N, a nitrogen analog of an aldehyde or ketone. The mechanism of imine formation involves the nucleophilic addition of the amine to the carbonyl carbon, forming a stable intermediate species called carbinol amine. Carbinol amine are compounds with an amine group in a group and a hydroxy group attached to the same carbon. Carbinol amine are analogous to the hemiacetal. Mechanism of carbinoamine formation. Carbinoamine formation begin with the nucleophilic attack on the carbonyl carbon. The product of the attack is a neutral, charge-separated species. Water and its conjugate acid both play a role in the reaction to produce carbonyl amine. You can see here in the mechanism illustrated below, the protonated water acts as a bonded acid, which it will become a nucleophilic attack on the negatively charged of oxygen of the intermediate on the protonated water. Whereas water as a bonded space, in this case, nucleophilic attack of the oxygen of water on the proton of the positively charged amine. Reaction of aldehyde and ketone with secondary amine. Aldehyde and ketone react with secondary amine to form enamine. Enamine is a compound that have a nitrogen bond to a carbon, which is a part of C double bond C double double bond. The mechanism involves nucleophilic addition of the amine to the carbonyl to form a carbonyl amine. Enamine formed only if the carbonyl compound has at least one hydrogen on a carbon adjacent to the carbonyl carbon. Formation of the alkene may be recognized as an elimination reaction. Irreversible addition of aldehyde and ketone. Aldehyde and ketone undergo addition reactions which are essentially irreversible. These reactions are This reaction use organometallic reagent to add alkyl group to the carbonyl carbon atom. These reactions are nucleophilic addition. This means that the organic group added is acting as a nucleophile in the reaction. We are accustomed to the nucleophilic behavior of alkyl group, example carbocation. But how does an alkyl group act as a nucleophile? This example below illustrates how this scenario happened. The alkyl group act as if they were free carbanion. Organometallic reagent. The actual structure of Grignard reagent in solution is complex. These reagents are always prepared in thereafter solvent, and in fact two ether molecules are associated with the Grignard reagent. Grignard reagents are prepared in diethyl ether. Grignard reagents are highly polar compound are a very strong Lewis bases. Mechanism of Grignard reagent to a carbonyl compound. Lewis acid-base interaction between basic carbonyl carbon and magnesium make the carbonyl carbon more reactive toward the alkyl group. The product of this reaction step is a halomagnesium alkoxide. Addition using organometallic reagent. Formation of alcohol via addition of Grignard reagent to aldehyde and ketone is carried out in two separate steps. Step 1. Addition of the nucleophilic alkyl group to the carbonyl carbon added by Lewis acid interaction between and the carbonyl carbon. The product of this step is halomagnesium alkoxide. See previous slide. Step 2. Protonation of the alkoxide oxygen. The product of this step is an alcohol. Step 2. This is represented by the step 2 illustrated below. This notation makes it clear that the overall reaction occurs in two separate steps. Notation 1 and 2 here clearly show that reaction occurs in a two-step mechanism. Primary, secondary, and tertiary alcohol may be formed in the reaction of aldehyde or ketone with Grignard reagent. Primary alcohol from formaldehyde. It also consists of two-step mechanism. Secondary alcohol from aldehyde. It also involves a two-step mechanism. Tertiary alcohol from ketone. It also is produced by two-step reaction mechanism. The net effect of the reaction of a Grignard reagent with an aldehyde or ketone in the addition of the compound R and H across the C double bond O double bond compared to the nucleophilic addition of HCN. Grignard and nucleophilic addition of HCN. Nucleophilic attacking the carbonyl carbon. Nucleophilic attacking the carbonyl carbon is being attacked by the CN, whereas it's being attacked by the hydrocarbon. A separate step is needed to produce the alcohol from the halomagnesium alkoxide. One pot reaction, multiple step mechanism, but all components may be added at once. For Grignard reagent, the reaction is irreversible, whereas for the nucleophilic addition of HCN, the reaction is reversible. Addition reaction to aldehyde and ketone using Grignard reagent are among the most important reactions in organic synthesis. These reactions are carbon-carbon bond-forming reaction. The net result of the reaction is the addition of the element of RH across the C double bond O double bond, which is being illustrated in the example below. Other metal-based reagents may also add components across the C double bond O double bond in an analogous way. Metal hydride add H negative and H plus across the C double bond O double bond. Whereas we add HH to a double bond, we call the reaction as a reduction reaction. Lithium aluminum hydride and sodium borohydride act in a fashion similar to Grignard reagent. The hydride ion H that carry the negative ion act as the nucleophilic reagent, adding to the carbonyl atom of an aldehyde or ketone. The hydride ion, lithium aluminum hydride, is more basic than the hydride ion in sodium borohydride, and therefore it is more reactive. Some functional groups, which may be reduced by lithium aluminum hydride, are unreactive with sodium borohydride, for example, alkyl halides, also or nitro groups. Therefore, sodium borohydride may be used to reduce C double bond O double bonds in the presence of such group. Mechanism of acid catalyzed esterification. The steps of the reaction are familiar to us from aldehyde and ketone nucleophilic addition. It involves the following step: protonation of the carbonyl oxygen by the CH3OH2 carrying the positive charge, and then nucleophilic attack of the alcohol on the carbonyl group by CH3OH, and then the step is further proceed with the protonation of the tetrahedral intermediate by the CH3OH group. This reaction differs from addition to aldehyde in ketone in the next step in what happens to the tetrahedral intermediate. In acid-catalyzed reaction of aldehyde and ketone, the tetrahedral alcohol species formed in these three steps, protonation, addition, and deprotonation, is a hemiacetal. It may undergo further reaction, but the ultimate product will be tetrahedral addition product. In acid-catalyzed reaction of carboxylic acid, this tetrahedral species is not stable and undergo further reaction, ultimately producing a substitution product and not an addition product. Carbonyl C double bond O double bond is retained in the substituent product, is represented by the example shown here. Substitution versus addition. Aldehyde and ketone undergo addition reaction, whilst a carboxylic acid undergoes substitution reaction. Substitution is for aldehyde and carboxylic acid, whereas the addition is for aldehyde and ketone. In both reactions, a tetrahedral product is initially formed. The choice between substitution and addition depends on how good the leaving group, which is represented by X, is. For aldehyde and ketone, X represents the R or the hydrocarbon or the H. It cannot act as a leaving group. For carboxylic acid, the H is being the S group is being represented by OH protonated, which is being protonated to OH2 carrying the positive charge, which can act as a leaving group. This is an example of tetrahedral, which can representing the intermediate product. Ionization of a proton from the alpha carbon of an aldehyde or ketone via attack of a bonded base result in the formation of an ion called enolate. Compared to the ionization of a proton further removed from the C double bond O, C double bond O bond. H here represent a not acidic, whereas H hydrogen which is represented by the purple color here, which is referred to alpha hydrogen acidic. Hydrogen and on carbon atom not adjacent to carbon can form resonance stabilized conjugate bases. Enolate ions are resonance stabilized. The extra stability afforded the conjugate base by resonance stabilization make the alpha hydrogen of an aldehyde or ketone more acidic than an alpha hydrogen on a compound which can form resonance stabilized intermediate. But this can be the whole picture. It's oxygen electronegativity that make the difference. Delocalizing charge onto a more stable electronegative atom adds stability to the enolate ion. The polar effect of the C double bond O dipole also stabilizes the enolate ion. Reaction of enolate ion. Enolate ion are bonded base, whereas this example illustrates how the enolate ion are present as a Lewis base nucleophile. Molecular orbital of enolate ion. The two highest occupied molecular orbital of the enolate ion are shown below. Note that this higher energy orbital is distorted toward carbon, the node and the higher energy. In the highest energy occupied orbital, the oxygen has more of the negative charge, but the carbon has more of the orbital. This higher energy orbital is where the electron comes from when the enolate ion acts as a Lewis base. The lower energy orbital show orbital overlap over the entire ion. There are three of the enolate ion derived from the three 2p orbital involved in the overlap. The third not shown is an unoccupied anti-bonding orbital. So basically we have three molecular orbital. Reaction of enolate ion. How do we know whether the attack of the enolate ion will occur at the alpha carbon or at the oxygen? This will determine it. This rule will determine it. The first one, the molecular orbital picture tells us that the enolate electron which will participate in the nucleophilic attack reside predominantly on the oxygen. The orbital which participate in the nucleophilic attack is distorted toward the alpha carbon. Reactions which are dominated by charges and electrostatic interaction occur at the oxygen. Reactions which are dominated by orbital interaction occur at the alpha carbon. Reaction of enolate ion. Remember that resonance structures are not separate entities, but that the molecule is some weighted average of this structure. We can write the curve arrow mechanism using either resonance structure. Example, attack of the enolate carbon ion on a carbonyl carbon, which is being illustrated in the example below. Boosted basicity of enolate ion. When the enolate ion acts as bonded base, it may either the alpha carbon or the oxygen to attack a proton. When enolate ion attack proton, either CH bond or OH bond may be formed. If a CH bond is formed, the original aldehyde or ketone is regenerated. If a OH bond is formed, the product is an isomer of the aldehyde or ketone known as enol. So it's being represented in the example illustrated below. Formation of enol. The conversion of a carbonyl compound into its enol is an isomerization reaction called enolization. Ketone, which is being formed into enol, called in this process is known as enolization. For most simple aldehyde and ketone, the equilibrium concentration lies far on the side of the ketone. The reaction is catalyzed by both acid and base. The mechanism for acid and base catalyzed enolization are different. Stability of enol. Carbonyl compounds with alpha hydrogen are in equilibrium with small amount of their enol isomer. Acetaldehyde producing vinyl as alcohol. Simple aldehyde and ketone have very small equilibrium constant for enol formation. Esters are even less favored to form enol. Beta dicarbonyl compound form relatively stable enol due to resonance stabilized conjugation and opportunity for hydrogen bonding, whereas phenol is the ultimate enol. Its aromaticity makes it significantly more stable than its keto form. This is keto form. The enolate ion is the intermediate species in base catalyzed enolization of aldehyde and ketone. Ketone will undergo a reaction process to produce enolate ion and producing enol, which which is a reversible reaction. A protonated ketoenol is the intermediate species in an acid catalyzed enolization of aldehyde and ketone, which is represented by the illustration below. Ketone producing protonated keto or enol, and the final product is a enol. Implication of enol formation. In base catalyzed enol formation, enolate ion are resonance stabilized species in which the CCO linkage become trigonal planar and sp2 hybridized. This means that any chiral information contained in the aldehyde or ketone is lost upon formation on the enolate ion. In acid catalyzed enol formation, the alpha hydrogen is removed to form a trigonal planar sp2 hybrid CW1C bond. The chiral formation in the aldehyde or ketone is in loss in formation of the enol. This example illustrates the formation of enol. This show here is the starting compound. The chiral formation is lost here. This is presented here. So both enantiomer are formed. Aldol addition and aldol condensation reaction. Aldehyde and ketone undergo a reaction called the aldol addition to form beta hydroxyaldehyde and ketone, which is being illustrated in the example below. Under more severe basic condition or under acidic condition, the reaction proceeds. Dehydration to form an alpha-beta unsaturated carbonyl compound is called the aldol condensation. These reactions are addition-elimination reaction which proceed via acid and base mediate mechanism, which should be similar to us by now. Mechanism of the aldol reaction. The base catalyzed aldol reaction proceeds via an enolate intermediate. It starts with the formation of the enolate ion, and then the addition of the enolate ion to the carbonyl carbon of the second aldehyde molecule will produce this intermediate, and then the protonation of the addition of the addition product will produce the final product that produce as the final product. The acid catalyzed aldol reaction continues, and then the product will and then undergo protonation of the aldehyde, and then the deprotonation to form the enol. The next step is the addition of the enol to a second protonated aldehyde molecule, producing the final product. The beta-hydroxyaldehyde is deprotonated to form the aldol addition product, which is illustrated in the example below. Under acidic condition, the aldol addition product is not stable. Therefore, it undergoes acid-catalyzed dehydration to form the aldol condensation product. Aldol condensation also occurs under basic condition. Dehydration is more difficult in base because OH is a poor leaving group. Therefore, more concentrated base or heat is needed to help drive the reaction. Another point that need to be considered is that simple alcohol do not dehydrate under basic condition. Cross-aldol addition. What happens if an aldol reaction is carried out with two different carbonyl compounds? We will get four different aldol addition products which are possible and are represented by the illustration here. Synthesis with the aldol condensation. With what we know about the mechanism of aldol condensation, we should be able to deconvolute the origin of any aldol condensation product. Identify the carbonyl compound which was the enolate or enol compound. Identify the carbonyl compound which was attacked by the enolate or enol. Then ask the question, is this a feasible reaction? How complex will the product mixture be? This portion is attacked by the enolate or enol, whereas this portion here on the right hand side is from the enolate or enol. We can also identify the beta-hydroxyaldehyde or ketone which was formed from our starting material as the first step before the aldol concentration. As being shown in the previous slide, this portion will be attacked by enolate or enol, while this portion will form the enolate or enol as the product, which then being further illustrated in the example here. Competition in reaction of aldehyde and ketone. Which reaction proceeds faster? Often, the reaction to the carbonyl carbon proceeds faster because of the carbonyl carbon is a stronger Lewis acid than the C-double-bond-C carbon. Therefore, the carbonyl addition reaction usually proceeds faster. Who wins, thermodynamic or kinetic? In reversible reaction, the kinetically favored product eventually drains back to the more stable thermodynamically favored product, faster but reversible, whereas the carbonyl addition are reversible. Conjugate addition wins out. The example shown here, although the product is slower, but the reaction is reversible. Reversible carbonyl addition occur with weak base as nucleophile. Amine enolate derived from beta dicarbonyl compound. When carbonyl reaction addition are irreversible, carbonyl addition will win out. This here show the two type of addition which are faster and reversible, and this one is slower and reversible. However, in terms of irreversible carbonate addition, which is reversible will win out because the carbonate addition product dominates with more powerful nucleophile like concentrated OH that carry the negative charge. Michael addition. When the nucleophile in a conjugate addition to an alpha-beta unsaturated carbonyl compound is an ester enolate anion, this reaction is called a Michael addition. The first step of the addition reaction results in the formation of another enolate ion with the carbon alpha to the carbonyl group in the alpha-beta unsaturated carbonyl compound. Malonic ester enolate are particularly useful in Michael readdition because they are weaker bases than the normal ester enolate. This mechanism here show how the enolate ion are being formed using the Michael addition reaction. The enolate ion that is formed the addition reaction then goes on to deprotonate another molecule of the original ester. This forms the neutral addition product and regenerate an ester enolate an ion. Thus, this reaction is catalytic in base. Only a small amount of base is required compared to Claisen condensation which require one equivalent of base. Once the original base formed from ester enolate ion, the reaction proceeds without further needs of the base. So this here show the final product will have two type of product, which one is referring to the another ester enolate ion form, whereas another one is Michael addition product is formed. Synthesis with Michael addition. Working backward from Michael addition product, we can envision two ways of putting the molecule together. Which combination of starting material should we choose between which is represented by the purple color here or which being reaction which being starting material which is being represented by the blue color here. So we will choose the enolate ion which is less basic to avoid competition from carbonyl addition. Therefore, we choose the purple color here because the enolate ion that is less likely to undergo self-condensation. Uses of aldehyde. Formaldehyde is example of aldehyde if with a present as a gas. With 40% solution in water, it forms formalin, which is used in preserving biological specimen. Formaldehyde is used in embalming, tanning, preparing glue and polymeric product as germicide, insecticide, and fungicide for plant. It is also used in drug testing and photography. When reacted with phenol, formaldehyde forms bakelite which is used in plastic, coating and adhesive. Acetaldehyde is largely used for the production of acetic acid and pyridine derivative. Benzaldehyde is used in perfume, cosmetic product, and dye. It is also added to provide almond flavor to food product and also used as a bee repellent. Uses of ketone. The most common ketone is acetone, which is an excellent solvent for a number of plastic and synthetic fibers. In the household, acetone is used as a nail pain remover, and pain thinner. In medicine, ketone is used in chemical peeling and for acne treatment. Methyl ethyl ketone, which is one type of ketone, is non-chemically as butane, is a common solvent. It is used in the production of textile, varnishes, plastics, paint remover, paraffin wax, and etc. Methyl ethyl ketone is also used as a welding agent for plastic due to its dissolving properties. Cyclohexanone is another important ketone which is primarily used in the production of nylon. So we come to the end of our slide regarding chapter aldehyde and ketone. Hopefully can get a bit of important concept regarding aldehyde and ketone. Have an enjoyable watching this video and have a pleasant day.